Hello. Welcome back. Today we do the last portion of trees as a part of our DSA series that we have been continuing. What is left is the AVL tree, the B tree, and the B plus tree. That's what we will cover today. We are tracking a syllabus that you see on the screen, and in this syllabus, we have completed typically the linked lists or the features of the linked list or the various kinds of linked list that we had to cover. We have also covered the various kind of trees like the binary tree, the threaded binary tree, the BST, and what is left out is the AVL tree, the B tree, and the B plus tree. In that, what we will do is for today, we will take all the three trees and then we will define the tree. We'll define certain properties of the tree, and then we'll work on the insertion logic of the tree. And finally, we'll conclude with the commonly asked questions. Now, if you talk about an AVL tree, then first of all, where is the word AVL coming from? And it's coming from two people who had discovered the tree, named after the inventors, Adels and Velsky and Landis. So that's where the word AVL has been acronymed of. Now, there are two important properties of the AVL tree that we need to remember. One, of course, it is a binary tree, right? So that is needless to say. So an AVL tree is a binary tree, number one. Number two, an AVL tree is also a binary search tree. And number three, an AVL tree will have the balance factor, which is defined as the height of the left subtree minus the height of the right subtree of any node, right? It could have 100 nodes or 10 nodes. Take any node. The height of the left subtree from that node and the height of the right subtree from that node should be such that it is an element of the set -1, 0, and 1. Right? So that means that the height cannot be too staggered in terms of the left subtree and the right subtree. You cannot just skew the tree just like that. And what I mean by skewing the tree is, let us take an example. Let us say that I want to build a tree with 1, 2, 3, and 4. Right? So let us see how do we build it. We take 1, 2 comes to the right of 1 because it is a binary search tree, I told you. Right? So, and then 3 will come to this side, and then 4 will come to this side because this is a binary search tree. So every right subtree should be greater than the node, and the left subtree should be less than the node. So in that sense, if I see this is a right skewed tree. If you don't know the skewed tree, please watch my previous lectures. You'll get the different types of trees that are possible. So this is a right skewed tree. And in this right skewed tree, if you see the height of this particular node, which is 1, right? So what is the height of this 1? From a height concept, again, we had defined this in the previous lectures, that if I am at a particular node, I will look down and till the last leaf node, till the leaf node which is at the largest distance from me. So in this case, there is only one leaf node, right? So 4 is the leaf node. What is the distance of that? When I say distance, we have to measure the edges that we traverse. So we traverse 1, 2, and 3. So we traverse 3 edges. That's why the height of the right subtree of 1 is equal to 3, because the edges are 3 to the largest or the farthest leaf node that we can actually imagine. Right? So the height of this is 3. And what is the height of the left subtree? There are no leaf nodes, right? So there are no edges. So if there are no edges, then that means the height of the left subtree is 0. So that is where the height of 1, so height of 1 from a right perspective is 3, height of 1 from a left perspective is 0. And if we subtract the height of 1 from the left subtree minus height of 1 from the right subtree perspective, we will be getting 0 minus 3, which is equal to -3. And this -3 does not fall under this set. That means this particular tree that we were talking about, this tree is not a AVL tree, right? So, and that's where we will now study how to make this an AVL tree. What are the things that we can do to make it an AVL tree? So I hope you have understood how to calculate height. And as we go along the way, we will calculate further heights, so you will understand better. So let us move on So again, summarizing, it has to be a binary tree. It has to be a binary search tree. Needless to say, I can say just binary search tree because all binary search trees are binary trees. So I don't need to define it to be a binary tree separately. And of course, the balance factor of each node, that is the height of the left subtree minus the height of the right subtree, should be part of the set of -1, 0, and 1. So that is what we mean by an AVL tree. And now let's see the various ways in which an AVL tree can be constructed, right? So there are some 3-4 use cases that we will try to understand, and from there we will take a live example and then we will solve it also. In fact, we'll take a couple of live examples and we'll solve it. So if I say that, let us say that I have a situation like this. So I'm taking this as the first use case, right? So this first use case that you see is saying that X is less than Y is less than Z. Let us say that that is how X, Y, and Z are defined. In that case, of course, then I will have to have Z at the top, Y here, and X here. That is how I'll have to define the tree. And this is again a left skewed tree, right? So this is a left skewed tree. Now, what is the height or the balance factor of Z? So let us see the height of the left subtree of Z. So the height of the left subtree of Z is the number of edges to the last node, which is the leaf node, or the largest node, that is to the leaf node. So that is basically 1 edge here and 2 edge here, right? So the height of the left subtree, from Z is equal to 2, and the height of the right subtree of Z, is 0 because there are no children on the right side. So then this two height difference, the height of Z from the left subtree minus the height of Z from the right subtree, is equal to 2. So my balance factor therefore is equal to 2. And this is not an element of -1, 0, and 1. So we have a problem, right? So the problem is that my balance factor is not good. While we can still say this is a BST, but BST is not the only condition for an AVL tree. It doesn't satisfy the second condition. So these were your two conditions. First condition was this, second condition was this. So while it satisfies this, it does not satisfy this. Hence it is not an AVL tree. What are the interventions we need to do? When it is, why is this problem coming? Its problem is coming because you moved left and you moved left. So you moved 2 times left. That is why this case is called an LL case, right? You move 2 times left. Then what we will do is we will rotate right from Z. So this is the rotation that we will do. So if we do this rotation, then we are actually trying to pull Z down, right? So we are trying to pull Z down and we are trying to push this up. This is what we are trying to do, right? So if that happens, don't you think this will be the nature of the tree? Y, X, and Z, because Z will come down, Y will go up, right? So this is the nature of the new tree that will be there. And that is what you see here. That is, after this will be the situation. Now calculate the balance factor for Y. Balance factor for Y is 1 minus 1, which is 0. Balance factor of X is 0 minus 0 is 0. And the balance factor of Z is 0 minus 0, which is 0. So all the nodes are actually balanced. Everybody is happy and we have an AVL right now. So that's on use case 1. Now if we go to use case number 2, let us see what comes out. So for use case number 2, so for use case number 2, it's just the reverse of 1, where we will say that, okay, we have X greater than Y greater than Z. If that is the case, then Z will be the root, and from the right of Z, we will create Y, and then we will create X, right? So this is a right skewed tree, right? So this is a right skewed tree. In this right skewed tree, what is the balance factor for Z? Balance factor of Z is left child is 0, right child is, we see 2 edges to go to the largest leaf node or the farthest leaf node, and that's why we will say 0 minus 2, which is my minus 2, which is not an element of -1, 0, 1. Hence, I have a problem with Z. I don't have a problem with Y, by the way. Why? Because Y has this balance factor for Y is calculated as 0 as the left child and right child is 1. Right, so we have -1, which is an element of -1, 0, 1. So I don't have a problem with Y. Neither do I have a problem with X, because this is 0 minus 0, which is also an element of -1, 0, and 1. So I don't have a problem with any of these nodes. I just have a problem with Z. If I have a problem with Z, then what I will do is I will do a left rotation from Z. Right? So if I do this, what will happen is I'm trying to pull Z down and push Y up. Right? So that's how I'm trying to do a anti-clockwise rotation of Z. If I do that, then this will be the situation of the tree. Z, Y and X. Right? And here the Y balance factor for Y is 0 because it is 1 minus 1. Balance factor for Z is 0, 1 minus 1, and the balance factor for X is also 0. The balance factor for Z is 0 because it is 0 minus 0, and X is also 0 because it is 0 minus 0. So everybody is happy. We have this kind of a situation now, and hence we converted a non-AVL tree like this to a AVL tree like this. Right? So, and that's why we call this as an RR, because we had created R here to create the problem. Right? The problem was created because it was R and R. So that's why we have an RR. So that's our second case. That's our second case. Now let us consider the third case. The third case will be when we have a left and right combination. So we have a left and right combination means that we will have, let's say, Z is less than greater than Y, and Y is less than X. Right? So Z is greater, our Y is less than Z, and our X is greater than Y. Our X is greater than Y. If that situation exists, this actually implies what? This actually implies that Y is less than X is less than Z. Right? So if this implies this, then, and we have got a tree like this, then this tree is not balanced. Why? Because the balance factor for Z is left child of, or the left subtree of Z is 2, minus right child is 0. Right? So the balance factor is going to be 2, and that 2 is not an element of minus 1, 0 and 1, and which is why we will say that this is unbalanced. So if it is unbalanced, then what we need to do is, in such situations, for an unbalanced tree which is created because of the problem of going left and going right, what we will do is we will do a left rotation like this. I'm sorry, actually we will be doing a left rotation like this. Right? So we will not do it from Z, because the imbalance has come because of the jaggedness of the edges. The edges are not going in one single line. They got jagged and got pointed like this. So from this pointed area is what we need to actually make the rotation, and that's what we are trying to do here. So we will rotate it from here in that sense, and this rotation will be called as a left rotation. Right? And this is a special case, unlike the last two cases where you saw that only one rotation was needed, because last two cases we saw that we had to rotate it right or we had to rotate it left, only one. But here we'll have to rotate it 2 times, and I'll tell you why. I'll come to that. Let us rotate this first. Right? So let us rotate this first. What we are trying to do, we are trying to rotate it left, which means Y will come down, X will go up. Right? So that's what we will do. So then Z is here, X is here, and then Y is here. Now this is what? This is a left skew tree, and this is created because of what? Left. So if it is created because of left, you know that you have to rotate right Z through Z. Right? So then the second rotation now starts. The second rotation is this. So the second rotation, you can easily understand that it is because that you now have a use case 1 matching, which is LL. You will have to do the rotation right. So this is the right rotation we have to do. So for a LR, we have to do a left rotation first and then a right rotation first. Right? So that's what this is trying to tell you. So if we do a right rotation, then our situation will be that we will be pulling this down and we will be pushing this up. So if that is the case, then this will become X, Y and Z. And if you see, that's what we had said, that Y is going to be less than X, yes, and then Z is going to be greater than Y. So we have achieved what we wanted to do, and all of these nodes are having a balance factor which is satisfying the condition for an AVL tree. So just remember that when it is LL, when the letters are the same, LL, RR, letters are the same, do one rotation. And that rotation will be in the opposite direction of these letters. Right? So if it is LL, letters are the same, do the rotation in the opposite direction of the letters. Letters is left, opposite direction is right. So do the rotation right. If it is RR, letters are the same, do the rotation in the opposite direction. So opposite direction is left. If the letters are mixed, then do the rotation in the same sequence as what you see in these letters. The letters say left, right, do first left, then do the right. And the left you will do it in between the edge. The edge is where you will do the left. And the right you will do from the top. Because the right will anyways match with this particular scenario. Right? So that's what we are concluding from here. Now the last use case that we have is when we will say that, so this is also done. The last use case is a right-left case. So we have a Z, we have a Y, and we have an X. So what does this mean? This means Y is greater than Z, and it also means X is less than Y, which in turn means Z is less than X is less than Y. Right? So if I have this kind of a situation, then this situation is creating an imbalance because of this right-left rotation or this right-left movement. Right? So the right-left movement, because the letters are different, I told you letters are different, do the rotation in the same direction as the letters. So we will have to do a right rotation. And why is that imbalance? Because Z is imbalanced. Z has a left as 0 and the right as 2. So balance factor becomes -2, which is not a part of that set. So therefore we will have to do a right rotation. So we have a right-left problem for which the solution is do a right and then a left. And this right has to be done at the crisscross section. So the crisscross is here, right? So we have to do the right here. So we will have to do a right like this, right? So if we do the right like this, then what we are trying to do? We are trying to move this down and move this up, right? So that will mean that we will actually be creating a situation with Z, with X and with Y like this. Now what did you land up with? You landed up with this situation. You landed up with an RR now. Right? So RR means that you'll have to do, letters are the same, so you'll have to do the ulta rotation, right? So ulta rotation means you'll have to do a left rotation, and that is what this also says, that you'll have to do a left rotation, right? So both the rotations that you'll have to do is coming from this particular concept or scenario. So if you do this kind of a rotation now, then what will happen? You are pulling this down and you are pushing this up, right? So that will mean that X will go here, Z will go here, and Y will go here. Right? So did you achieve what you wanted to? Z is less than X, yes, and Y is greater than X, yes. So that is what we did with this RL kind of a problem that we created. We have therefore established that we'll have to do a right and a left, because when it is RL, letters are different, we will do the rotations in the same direction as the letters, right? So that's the way in which you should probably, or I remember things. Right? So that's the fourth use case, and using these 4 cases we will now try to solve certain problems. So let us see first one case which is a bit large and it will take some time, so bear with me, but then we will also solve a simpler case also after this. So it says that insert the following keys into an AVL tree in the given order. Excellent. We will insert it, and once that is inserted, it also says that clearly mention different rotations used and balance factor of each node, right? So we will also have to mention the rotations that we are doing. So as we go along the way, you will be mentioning the rotations that is actually happening. You will draw the tree, you will draw the rotations, you will say LR, or RL or LL, RR, and then talk about the rotations that you are doing. That I'm sure you can do. I'll not be going to that level of depth. What we'll start with this. So let's start with 12. So 12 is our first node. There was nothing, so we started inserting 12. Right? So next we will insert 11. 11 will go here. Next we will insert 13. 13 will go here. What are we doing? We are taking one node from sequentially from the problem given. Mind it, we are not going to change the sequence from the problem given. We have to take the problem sequence the same way and try to build a BST from it. All we are doing is we are building a BST, right? So once we have built a BST, this BST is an AVL also, because all this particular node has a balance factor of 0. This has a balance factor of 0. This has a balance factor of 0. So that is why this is also going to be an AVL. Right? Now, till the time it is an AVL, you keep on inserting. If it is not an AVL after the insert, then now start doing the rotations. That is the funda. Right? So we will now insert 10. So where is going to 10 going to go? 10 is going to go here. Now let us see what is the balance factor for 12. Now balance factor for 12 is the left side is going to give you 2. The right side is going to give you 1. Right? So 2 minus 1 is 1. So this is okay. We are still okay. We are still good. Right? So that's where our balance factor here is justifying that we are in the right track. Right? So next what we will have to do is we will have to figure out the next element is I think 9. Yes. So we will have to insert 9 here. Right, so 9 is inserted. Let me mark this: 12, 11, 13, 10, 9. So all this is done. Now 9 creates an imbalance. Where does it create the imbalance? Now the imbalance is created, just check node number 11. So what is the balance factor for node number 11? Node number 11 has 1 and 2 on the left side. So 2, and on the right side it has 0, right? So 2 minus 0 is 2. So 2 is not allowed. Right, balance factor 2 is not allowed because we are allowing only minus 1, 0 and 1, right? You saw in the last slide. So that's why this has created a problem. Now if this has created a problem, investigate only this from this point, the tree. Investigate this tree. What does it look like? Doesn't it look like left left? It looks like left left, right? So if it is left left, what were you supposed to do? You were supposed to make a ulta rotation. Both letters are the same, so you are supposed to make an ulta rotation from the top. Right, so that's what you will do, an ulta rotation. So do that. What does the tree become? The tree becomes 12. Then because you will be pulling 10 up, 11 down, so 10 will come here, 11 will go to the right, and 9 will go to the left, and 13 was anyway there. So that is going to be your balance tree. Check any node, you will see that the balance factor is perfectly aligned in terms of what is acceptable. Now insert 15. Now 15 is the next item. So 15 goes here. So 15 is perfectly fine because it doesn't change anything. Let us see if it changes. Let us see 12, right? 12, what is the left side of the 12? Left side of 12 is having 1 here, 1 here. So 2 is the height of the left subtree and 2 is the height of the right subtree. So 12 is basically balanced. So there is no imbalance in the entire tree. You can check all the other nodes. There will not be a single imbalance. Now let us take 14, the next item. So if we take 14 as the next item, then 14 is supposed to go to the left of 15. Right? So when it goes to the left of 15, there will be an imbalance. Let us see the imbalance of where it is created. So I think the imbalance will be here. Let us check that. So 13 on the left side has what? 0. On the right side has what? 2. Right? 0 minus 2 is minus 2. It is not allowed. Right? So that is why we now have an imbalance here. Now why did this imbalance come? This imbalance came because we did a right left. Right? So if we do a right left, letters are different. Letters are different means 2 rotations. 2 rotations means in the same order as the letters. So do a right, but the first rotation has to be done on the edge, right? On the junction point of the 2 nodes. So what we will do is we will do a right rotation, but we will do it here. So when we do this right rotation here, then this 14 will come to the top. So basically we are talking about this particular subtree. Right, so we are talking about this particular subtree because the right and left are touching these 3 nodes. So this particular subtree, right? So 13 was the problem. So from 13, whatever is the subtree is what we are taking, right? So 13, 15, 14 creates a problem, a right left problem. We will rotate it right at 15, right? So if we rotate it right at 15, then this is what will come: 13, 14 and 15 when we rotate it right at 15. Right, so I hope you understand from the previous slide. You can understand how I achieved this. And then this is basically a right right. So if it is a right right, then we will have to do a left rotation from 13. So if we do the left rotation from 13, then our final tree will look like this: 12, 12. Sorry, let me wipe this. Yeah, so 12. Then we have 10. Then we have 9. Then we have 11, and on the right of this, be careful, we are doing a left rotation. 14 will move up, so 14 goes up, 13 goes down, and 15 goes right. So that is what you will achieve once you have balanced out on the 13 node, which was -2. So that's going to give you 12, 10, 14, 9, 11, 13, 15. Right? So now everybody is balanced. So I hope you understood how we did the two steps. So we did the first step here when we did a right rotation. And that right rotation made us having a right skewed subtree, which was a right. And for right, we know we have to do a left rotation. So that therefore, for a right left, we know, of course, we know that right left means two rotations, one right, one left. Make a point that right has to be from in between, and the left, the second rotation, has to be from the top. And that's what we have done here. We have achieved this particular tree as of now. So that is your 15, that is your 14 getting added. Now let's add 18. Now 18 will go from 15, we will have to add 18 here. Now does it create any imbalance? Let us see. 15 no imbalance, 14 no imbalance, 12 no imbalance. So there is no imbalance as such that this particular node creates. You can easily check it out. Let us go to the next node, which is 7. Right? So 7 will be inserted to the left of 9. 7 gets inserted to the left of 9. Now does it create any imbalance? 9, there is no imbalance. 10, there is no imbalance. 12, there is no imbalance. So there is no imbalance here. Let us insert 6. 6 will be inserted to the left. Right? So if 6 is inserted to the left, let us see if there is an imbalance. I can see an imbalance at 9. Right? So I can see an imbalance at 9 because here you have 2 edges to reach to the leaf, and here you have 0 edges. So this entire subtree is actually skewed, and this entire subtree is giving you as 2 as your imbalance factor. And because this is giving you 2 as your imbalance factor, it is not allowed. Therefore this entire subtree will have to be balanced using rotations. What rotations? Why this imbalance came? Imbalance came because of left and left. That means you will have to move this right rotation. Letters are the same. If it is same, then do ulta from the top, right? Right rotation. So if you do the right rotation, your tree will look like this. Your tree will look like 12. From 12, you will have 10. And then 7 will move up. And 9 will go to the left. And then, 6 will go to the left. And then 9 will go to the right. So that is what will happen here. So 6 will go to the left and 9 will go to the right. So that is the imbalance part of it. 10 already had 11. And finishing the right subtree, it had 14, it had 13, it had 15, and it had 18. So this is your current tree, and the current tree is balanced. Right? So now the next thing is that we will have to bring in is 5. So 5 definitely will go here. Right? So 5 will go here. And because 5 goes there, does it create any imbalance? We have an imbalance at, let's say, if I see 10, yes. If I see 10, 10 has an imbalance. Why? Because go to the last leaf. So 1, 2, 3. That is what 10's left subtree height is. And 10's right subtree height is 1. So 3 minus 1 equal to 2. So that is an imbalance. So this imbalance that we have needs to be now rectified. So if this imbalance that is happening at 10, why does it happen? That's what we will need to understand. So the imbalance at 10 is happening because you have, let me do this. So this is my tree that is an imbalance. So the next tree that we will cover is B tree, and in order to understand B tree is also an AVL tree. So an B tree is also a binary search tree. My bad. It's also a binary search tree, but a different kind of binary search tree. Now, before we get into the definition, let's see what is the problem, right? So we are trying to see that if this is the tree node that we were aware of, right? If we talk about a standard binary tree, right, which is a BST, right? We are talking about a BST. Then this is, let's say, some value x. Then from the left child, we can actually create y here, which is less than x, and hence it goes to the left child. And from the right child of this, we can create z here, which goes to this, which is the right child of x, and we can extend this the way we want, right? So, but this is a normal BST represented through a double linked list. We have seen this again in the last lecture. Now, if I am here and I want to know y and z both, then I will have to first go here, come back, and then again go here. I cannot come back unless I do a threaded binary tree. Again, my previous lecture talks about that. So I'll have to again restart from here and go to the right and get my z. So that becomes a problem. So if I have to go to the hard disk, and get the maximum amount of data I can extract from a page memory, right? So my hard disk is here, and inside the hard disk, there will be a lot of page memories like this, right? And each page memory will have a lot of data. So if I have to extract that data together, not just one node of data, I want this entire data one shot, I will not be able to do it because I don't have the capability to do it. My data structure doesn't allow me to do it. Therefore, if somehow I could have got both x, y, and z in the same place, in the same node, then my life would have been easier. And that is exactly where B tree comes in. It gives you the capability to get more data from one node, right? So that is what we will now see. So if I talk about, let's say I will talk about m equal to 5. What is m? M is called the degree. What is degree? We will come to it. Let us take m equal to 5, or degree, or we call it as order also. Now if m is 5, then actually in one node we can contain 4, which is m minus 1 keys. When I say keys, that's the data we were talking about, right? We wanted a lot of data together. Those are the keys, right? So how does that key look like? This is how it looks like, right? One key looks like this. Let's say that is A. The key is A, right? Or let us say that I will generalize this to say that this is K1, right? So this is my K1 node. So if this is my, in fact, this is K1, not K1 node, because the node is only one, this large rectangle that you see. That's the beauty of B tree, right? It creates a large node and puts the smaller keys inside that large node. So we have a key here which had a left subtree and a right subtree from our previous binary tree examples or BST examples, and that's the node that we have put here. Can we replicate this? Can we say the next key is like this? And in that next key, we will have this as the left child, right child, and this will be my K2. Can I say this is my next key, right? This is my next key, which is having same thing, left child, right child, K3. Then can I say we have the next key, which is again having my left child, right child, and K4. And the last, we will say that we will have this as the last area, which will have a left child, right child, and it will have K4. So this entire thing is my key, right? And this entire thing is my node. Sorry, my bad. And inside that we have the keys that we talked about. And these keys, the smaller versions of these keys are actually the double linked lists that we had used in our binary search tree. I hope you can understand, with each left right pointers. So if I have a situation like this, then can I say that from here there can be a situation where I can have a node which has, let's say, L1 as a key here, or C1 we will call, let's say C1 as a child, right? So we will call this as a C1 child, and this is here, right? So it also has a left and right, and it has only one key. Let's say it has only one key. We can put more keys. We know that we are talking B trees. In one node we can put more trees, but I am assuming in the child only one key, right? Just for you to understand. And then from here this will be, what is C1? C1 has to be less than K1, right? So because we are talking binary search tree, I told you this is also a binary search tree. So we are talking C1 to be less than K1, and hence C1 is attached to the left child of K1, right? So similarly, the right child of K1, we will have C2, and this C2 will be greater than K2, right? C2 will be greater than K2, but C2 will also have to be less than K2. C2 will be greater than K1, my bad. C2 will be greater than K1, right? C2 will be greater than K1 because it is attached to the right child of K1. But at the same time, it is also attached to the left child of K2, right? Because there is no difference between this part and this part, right? So both of them are pointing. One is pointing, saying that I am the right child of K1, and the other is saying I am the left child of K2. But both are the same. So what we will say, we will remove this boundary, right? And we will say that this particular line is actually treated as C2 is greater than K1 and C2 is less than K2. C2 is less than K2. So let's move on. So we understood that we are having a single pointer here to the C2, both as a right of K1 and as a left of K2. So likewise, if I come here, then K2's right and K3's left are all one the same. So there is no difference between this point and this point, and hence we can say that this is the same. So therefore we have here K3, and therefore we can now attach a child, let's say C3, and this C3, if I attach my K2's right to C3, that means C3 is greater than K2, right? And C3 is also less than K3. So that is something that we are achieving out there. The next thing that we are also achieving is when we put the next child, which is our C4. So in this C4, we can definitely say that these two blocks are the same, pointing to the same region. So we can eliminate this and convert it into a single pointer. And that single pointer will therefore now start pointing from here to here. So that is our C4. What can we write about that? C4 is greater than K3 and C4 is less than K4. All we are doing is we are maintaining the binary search tree, right? So wherever we are attaching it, we are actually saying that whether it is to the right or left of a parent, accordingly we are trying to adjust the signs and trying to say that this is greater or this is less. Similarly, here we don't have these pointers as duplicate pointers. We will create only one pointer here, and in that one pointer here we will be attaching K1, K2, K3, K4. In fact, we had to stop at K4 because we said we will have m-1 keys, right? So which is equal to, we said we will have 5, so we will have 4 as m-1 keys. We already have till 4, we don't need the last node. So we had created this by error, so we will remove it and we will just close this off with the right pointer. So the right pointer here will actually be pointing to the C5, and this C5 child will have the property that C5 is greater than K4 because C5 is the right pointer. So this is how we have converted a 5 let's say nodes, singular nodes into one compact area, right? So we had converted, the 4 singular nodes into one compact area. And if you see, we have 1 child, 2 child, 3 child, 4 child, and 5 child. So our M is actually equal to our children, right? So 5 is actually equal to the children, and our keys is actually equal to M minus 1, which is equal to 4. So this is something that you'll have to remember from a binary tree definition standpoint. And what we have done is, we will, if we summarize it quickly, then we have taken a parent node where we are saying that we are capable of now storing multiple, let me remove this, then you can probably understand better. Yeah, so let me bring this here. So we are saying that we can now create something which is having multiple nodes, multiple values in one, or keys, right? So multiple keys is what we will have to tell from a parlance perspective, multiple keys in one single node, right? So that is what the essence of B tree is. So we have created K1, we have created K2, we have created K3, we have created K4 in one single node. And this left area will point to a child C1. This is the right of K1. This will point to C2, which is also, C2 is greater than K1. Yes, C2 is greater than K1 because C2 is to the right of K1, but C2 is to the left of K2. So C2 is less than K2, right? So that is on the C2 side. Similarly, we can say our C3, which is greater than K2, C3 is greater than K2, and C3 is less than K3 because it is also the left pointer. So while this line is the right of K2, this line is also the left of K3, right? So it will satisfy both the conditions. And therefore, next line is C4, which will take me to the child, which is C4 to the right of K3. C4 is greater than K3 and C4 is less than K4 because also it is to the left of K4. And the last line that we have is connected to the last child, which is C5, and this C5 is actually my greater than K4 because we are at the right of K4. This line is at the right of K4, so we are talking right of K4. So this is how we actually conceive a binary a B tree. And remember, the B tree is also a binary search tree. All we are saying is we are compacting the nodes into one single node, so that, like I said the example, right, go to a disk, go to a memory block, you'll get multiple data from there instead of going around the place and searching for the data, right? So the more you do, more keys you put into a node, more complicated it becomes, more traversal complicacy may increase in terms of hunger of the memory required for it. But then it increases, or it saves on the cost of the CPU because you have to go only once there, right? So that's the trade-off that we'll have to do, but that's not something that we will discuss. If we go to the properties that we discussed just now, right, you will see that this particular tree that we are talking about, the B tree, the maximum children we said is the order, right? So the order is equal to M, which is also called as the degree, and this signifies the maximum children, right? So for a node which is having, let's say, 4 keys, we can have 1, 2, 3, 4, 5. So 5 children we can have, which means M is 5, right? So we can have these 5 children. So this is on this. Maximum keys that we can have is 1, 2, 3, 4. For a node with M equal to 5, that means this is equal to 4, which is equal to M minus 1. So the maximum keys that we can have is M minus 1. Now, minimum children that we can have, these are the maximum, but is it always necessary for it to hold these many? Not necessary. It can hold a minimum number of keys, minimum number of childs also. So the minimum number of children that it can hold, and for of course, root here is treated in a special manner. The root has a special formula. We'll come to that. So when I say minimum, I'm talking about all the non-root nodes, right? All the non-root nodes, if we see the minimum number of non-root nodes, minimum number of children for a non-root node is actually M by 2 and the ceiling of that. So minimum number of non-root nodes. Minimum number of non-root nodes is M by 2 and the ceiling of that. So if we have m as 5, then m by 2 is equal to 5 by 2, and the ceiling of that is equal to 2.5. Ceiling of that is equal to 2. Right? So the ceiling is 2, which means that the minimum number of non-root children is 2. So I need to have at least 2 children here. That's all I'm saying. And it need not be here and here. So it can be here also. So we can take this and put it here also. It all depends how the BST is shaping up. But we need to have 2 in this level. That's all we are saying. We need to have 2 in this level. Similarly, the minimum number of keys will be m by 2 minus 1, the ceiling of that. So minimum number of keys for non-root nodes will be m by 2 minus 1, which is 2 minus 1, which is 1. So I can have minimum 1 key in a non-root node. So if I have some situation like this, let's say, if I have a situation like this, then this minimum number of non-root node I can actually populate is 1, which means if I populate here one element, that is sufficient. So I'm talking what? This is a non-root node, and here what is this? This is a key. So I'm talking 1 key here. So this is the minimum number. I don't need these 3 blocks to be filled. I can just fill 1 block, which is sufficient. Right? So that is something that I wanted to highlight when we talk about minimum keys for the non-root. Now for the root, I was saying that the root is a special case and all of that. Right? So if root is a special case, what is the special case? In root, the minimum number of keys is 1. So I can create a root with the minimum key as 1. So I can create a root like this. Perfectly fine. It will have a left child and a right child. That's it. And the root's minimum children therefore will be 2. The root's minimum children will be 2. So one root needs to have 2 minimum children. Now these can have any number of keys, which is okay. But their minimum children will be 2. So those are the root min keys and the root min children. And if the root is a leaf, then it may have 1 to m minus 1. So if the root is only the root, there is nothing there. So again, it will follow the same funda of this. That is m minus 1. So it can have m minus 1 from 1 to m minus 1. Any number can be here as the keys. So that's on the root as a leaf. The keys definitely will be in order, which means that if I have created a root like this and I'm pushing, let's say 7, 18, 20, 25, 30, this order has to be maintained. Right? So because we are talking binary search tree, etc., we have to have the root, the key orders has to be sorted. The key child rule, we have already seen this in the last example, how the children are less than or greater than the K1, K2s, etc. Leaves at the same level. So after we create everything, all the leaves will be at the same level. After we create a B tree, all the leaves will be at the same level. So the next thing that we need to talk about is the overflow rule, and we will come to this when we see an example. So we'll split the nodes when the keys become equal to m, because m is not allowed. So in case you have m as because keys are not allowed rather. So in case you have m equal to 5, how many keys can you have? You can have m minus 1 keys, which is equal to 4. So in case you have 5 keys in a particular node, then what do? You'll have to split it. You cannot have 5 keys in one node, and that's something that we will see. And the split behavior is also something we'll talk about, right? We'll promote a median and all that we'll talk about. What this table is actually talking about is the properties of a binary tree. So this question typically comes properties. So you'll have to remember the relationship between children, keys, root, the order, and the splitting logic. Splitting logic we will see in details in the next slide when we actually build a B tree. Now the promotion, the split, all this we will talk about in the next slide. And the search complexity, if we see that because we are actually having the number of nodes broken down, whenever we break down, whenever we divide and conquer things, it has to be a factor of log, right? Mostly it will be a factor of log. So the search and the insert complexities of this tree will be an order of log n. Now if I see what is the construction so that we can jump into that concept of splitting that we talked about in the properties. All right, so we will try to figure out or establish that how do we split a tree or how do we split a node when it actually gets overflown. Those are the concepts we'll try to gather. And in order to do that, we'll have to first start with the construction of a B tree with the elements that are given to us. And these elements are given to us in an order, right? Not necessarily that this has to be ordered, but while we place it into the tree, we'll have to order it. In our case, this is given as an ordered tree. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll have to create a B tree from it. Remember, this is also important. They will give you this, that this tree has an order of 4. So what is the max children? The max children for this tree will be equal to M, which is 4. The max keys that we can have is equal to 3. And we will move with that. We will move with these two concepts. So step by step, if we see, say first thing we will do is we will take a 3-boxed rectangle, and this is our node. Why 3? Because we can take maximum 3. So we can take 3 elements here. So let us take the first element. Ho gaya. Second element, done. Third element, done. Remember, elements can only be inserted at the leaf, right? So this was always a leaf because there was no child. So till the time we positioned 1, 2 and 3, at every point it was the leaf. And therefore we went to the leaf, said, do you have a position free? Yes, I will position you there. That is what we did here. 1, 2 and 3 done, right? So we are done with these 3. Now comes 4. Now 4, when it comes, 4 is going to sit here temporarily. Sit here means it doesn't have a space. It is waiting for a space. And hence we will have to split this. So when we split this, then what we will do is we will find out the median of this particular list. What is the list? 1, 2, 3, 4. 1, 2, 3, 4 is how many elements? It is 4 elements. So if this is 4 elements, then I cannot find an exact midpoint. So I will find a median. So median can be 2 or median can be 3. So I can actually split it by half at 2 or I can split it by half at 3. So what I will do is I will split it at 2. Remain consistent. You either take the left or the right when it is even, right? Remain consistent. So we will split it at 2. And when we split, whatever is the split that we are doing, we will actually make sure that so whatever split we are doing, we will actually make sure that that split element, the rightmost element of the split, or whatever that element we are splitting, right, is actually going to the top. So we will take this to the top. Remember, we can have max 3 keys. So every node will have 3 blocks. And because we have split this, now this is gone, right? So now we have 1 to be positioned. So 1 is less than 2, so it will go to the left child. So again, this is a node, and this node again will have 3 placeholders, in which one of the placeholder will be this one. And then we have 3 and 4. Both 3 and 4 are greater than 2. So it will come through this line, right? So through this line it will come, and 3 and 4 can be positioned here. 4 can be positioned here, right? Because all the insertions can happen on the leaf as long as it is allowed. So we pushed 2 to the top and we adjusted 1 and 3, 4. So that is how we adjusted, or we moved on from this particular concept. So now the next thing is we have to bring in 5. So if we bring in 5, so we have to see the root. We have to always check the root. Even for a BST, the same funda we are talking about. That 5 is greater than 2. Okay, then go to the right. Now I have reached a leaf node. Okay, then I can insert. If I can insert, I will ask the leaf node, do you have a position? Yes, please come in. So it comes in 5. So that is how 5 is also done. Now 6. Now what happens to 6? Again you go to the root, right? So after you go to the root, you will say that 6 comes here because 6 is greater than 2. So So 6 finds a temporary placeholder. Now 3, 4, 5, 6 is an even element. Median of that we have to split, right? We cannot have 4 elements here. So we have to split this entire thing. Somebody has to go up. So 4 will go up. I said take the consistently the whatever approach you are saying. That medians can be either 4 or 5. We have been taking 4, right? The second element we are taking. So that we will move up. So if we have to move this up, then this 4 will take the root from here, right, and will move up, and it will get a placeholder. There is a placeholder here, right? So for the 4 to stay, so 4 will stay here, and because 4 has moved up, this is non-existent, right? So we will therefore now position 5 and 6 accordingly. So 3 is greater than 2, it is in the right position. Now we have 5 and 6. 5 and 6 has to be adjusted after 4, right? So 5 and 6 has to get a new node. So 5 will come here, 6 will come here. So that is how you will move things up and adjust the nodes. Next we have to bring in 7. So 7 comes through the root. So from here 7 sees that I am greater than 4. So I will follow this path and come here. Do I have a space? Yes, I have a space. So I will get myself inserted there. 7 is done. Let us take the next, which is our 8. Now 8 goes here, comes to the root, sees that it has to follow this path, and it finds a placeholder here as a temporary, which means we have to split 5, 6, 7, 8. If we have to split, median is this or this, we will take 6. 6 will find a place to go from here to the top, right? And the top has a space. So 6 comes here, and 6 goes there, means 6 does not stay here, and 5 is here, which is greater than 4. So we need a separate node to accommodate our 7 and 8. 7 and 8 is greater than 6. So 7 and 8 will come here. So that is how we are moving things at the top, creating a new node, adjusting the keys. So that is on your 8. 9 says that, okay, I'm going to come through this. I am going to go through this path, which is greater than 6, the right child of 6. So right child of 6 will take 9 here. So 9 gets a place here. And we have 10 here, which is the last element. In this, we have a problem. So the problem is that this 10 cannot fit in this particular key because it has already filled up its maximum keys. So it has to go up. So it goes up. It goes up, but the problem with that is that in fact it will not go up. My bad. We will figure out who goes up, right? So to figure out who goes up, we'll have to take 7, 8, 9, 10. So we'll now need to make 8 go up, right? So 8 will go up, but 8 cannot stay here because again this is filled. So we'll follow the same funda. We'll split this. So we have to split what? 2, 4, 6, 8. Right? So 8 we will remove from here because it has gone up. We are now trying to split 2, 4, 6, 8. So 2, 4, 6, 8, if we have to split, then 4 will be my median. So if 4 is my median, then 4 has to go up, right? So if 4 goes up, then 4 creates a new node at the top, which becomes my fresh root. So from 4, so I'm now trying to draw the new tree because the new node has been created at the root. So the new root, we are actually created a new root because 4 has to move to the top. There was nothing at the top, so we will create a new node at the top. So 4, what is now? We have to adjust this. So 4 has moved to the top, so we have to adjust 2. So where is 2 going to go? To the left of 4, right? So 2 to the left of 4. Now this is done. We have to adjust 6. So 6 goes where? To the right of 4. 8 goes where? To the right of 4. Right? So that is these two nodes. 1 goes where? To the left of 2. So those remain as is. So we will just draw them as is. So this is also done. 3 goes to the right of 2. 3 goes to the right of 2. So we'll take the next element as 5, but before taking 5, I think we have a typo here. So this should be 6, right? So this should be 6 because we were we were adjusting this here. So that is why this should have been 6. My bad for that. So 6 and 8 is here. We are trying to bring in 5. Where does 5 go? We'll always start from the root. This is right greater than 4, so it will go to the right. It is less than 6, so it will have to take the left pointer of 6, right? So it will go here. So this is where our 5 will go, right? So next element that we have is 7. Now where does 7 go? 7 goes to the right of 6, so 7 will go here. Next is our 9. 9 goes to the right of 8, right? So 9 goes to the right of 8, so that means we'll be creating something like this. So 9 goes here. And where does 10 go? 10 goes to the right of 8, which is here. So that is your final B tree. So always remember that when you are doing a B tree, then this final output that you got will be different if you don't select the median as 4, but you select the median as 5. That is the third element. So if we have done this with the second element, we have been consistent, we have chosen it, and accordingly we have got what we wanted. If you see, all the leaf nodes are at the same layer. That was one of the condition that we saw. So now if I go back to the promotion rules, now it will be clear. So I hope now this is clear. Leaves are at the same level. Yes, all the leaves are at the same level. Overflow rule, we will split the nodes when key is equal to m. We'll take that top. Split behavior, promote the median, remove it from the child. We have moved it up. That means we'll remove it from the children. Promotion behavior, promoted keys go to the parent only. And if the parent is full, it will create one more fresh key or a fresh node. Search complexity, we have talked about it. So I hope that part is now amply clear in terms of what I wanted to establish. But just spend some time here. So when we took this particular example and added this 10, right, that 10 will be pushing things to the top, and that top did not have anything. So 4 got pushed to the top. So 4 came here and created a new node. And from 4, we have been seeing how we can adjust 2. We adjusted 2 to the left. From 2, we adjusted it to the left, and so on, right? So, and then 6 when we took, right, we saw that it has to come to the right of 4. Then we took 8. So we will take all the nodes at a particular level, complete it before moving to the next level, right? So it's something that will probably help you not to mix things up. Not that you can mix things up by actually juggling levels also, you can do that, but I would prefer to probably finish off with 2, 6, 8 before going off to 1. In fact, we went to 1, we should not have gone to 1. We should have gone to 2, 6, 8. So 2 we have given, then 6 and 8 will go to the right of 4. Why? Because 6 and 8 comes here, and insertion always happens at the leaf. So when I draw 6, I have spaces for 8 and one more. So I will, when I get 8, I will insert it here, right? So now that is done. If I take 1, then 1 goes to the left of 2. If I take 3, 3 goes to the right of 2, right? So that is how we are doing. If I take 5, 5 has to find a placeholder. So come from the root. Root says 5 will be to the right of 4, and this should be to the left of 6. So then we create a new node, right? And then we have what? 7. Now 7 again come from the root. 7 is greater than 4. 7 is in between 6 and 8. So it should follow this line. So this line should create a new node for 7. Right? So that's what we do. And then we have what? Then we have 9 coming in. So 9 is greater than 4. 9 is greater than 8. So 9 will find a new node placeholder here. So 9 comes here. And 10 is greater than 4. 10 is greater than 8. So 10 will also follow the same path, come here and see that there is a space here and put it here. So this is how you get your final B tree, right? So I again recapped it, and I think it will be much clearer if we do one more example, and that example will be a example which is a which is not a sequential example, and there you will understand how we need to keep it in or bring it in sequence. So in this example, the uniqueness of this example is that it is not in a sorted sequence, unlike 1 to 10 that we did earlier. So here m is given as 4. So the number of keys that you can have is m minus 1, which is 3. So now if we actually take 3 keys and try to figure out how we do this with 3 keys, we will take a 3 key node and we will put in 34 here. We will put in the next key, that is 67. All these insertions are happening at the leaf because right now we just have one node, which is the leaf. So leaf can insert till it has space, and we have space for 3 keys. So we will insert the 3 keys. Right now comes 90. 90 comes here. So 90 says I want some space. 90 doesn't have a space. So what do? We will therefore need to create a split. So we have 34, 67, 89 and 90, and we are going to split at 67, which is our median. So 67 will go up. So we will just remove this from here and we will create a new node at the top, which is our 67. Right, so 67 goes to the top. Now when 67 goes to the top, please remove 67 from here, and in fact track it from the right side, remove everything from here. Right, so don't take the existing links because that will confuse you. The splitting, the node that is getting split, don't ever think that the earlier child links are valid. Redo those. Right, so we will redo 34, we will have to redo. It is to the left of 67. So 34 comes here. Then 89, we will have to do 89 is to the right of 67. And we have 90 is also to the right of 67. So this is also done. So till this point we are done. Now take 100. Now 100, where does it go? 100 goes to the right of 67. So 100 will go here. So 100 is done. 2, where does it go? It goes to the left of 67. But it can't go here because 34 is obstructing it. 34 has to make space because it has to be sorted. So remember we said inside the node the keys have to be sorted. So that's why 2 wants 34 to move to the right, then it comes inside. So 2 is gone. Then 36. 36 comes easily here. So that takes care of till 36. Now we will have to insert 76. Now 76 goes here, but then if we have to insert 76, we have to insert it here, right, to the right child of 67. So 76 actual place will be here because it has to be sorted, right, in the sequence, but it is a temporary place. So I need to see how I can split this particular right child. So I will say I have 76, I have 89, I have 90, I have 100. I will split it here. So 89 will go to the top. Right, so 89 will go to the top, which is fine. I move 89 to the top. Remember I told you, remove everything that is getting split. We will recreate everything, remove everything. Right, so I will remove everything. Now I have to bring in 76. 76 is between 67 and 89. So 76 comes here. Fine. Then we have 90. 90 is greater than 89. So 90 will go here. 90 is greater than 89. 90 goes here. 100. 100 is also greater than 89. Right. So 100 is also greater than 89. So 100 will also go to the right and it will find a placeholder after 90. So that is what this will look like after we have inserted 76. Now if we insert 53, where will 53 go? Now 53 will go here because that's the temporary placeholder. We are trying to place 53 here, right? So that this is what we have to split. So if we split this, then we will write this here 2, 34, 36, 53. Be careful, just make this sorted before you actually decide on the median, right? So 2, 34, 36, 53, you will have to move 34 up. 34 moving up means that 67 and 89 will have to move to the right. So we will move 89 to the right and we will move 67 to the right, and then this place becomes empty. 34 moves there, right? So 34 moves there, and now as I said, remove this split node, we will recreate it, right? Otherwise you will definitely land up into issues. So 2 is less than 34, so I will create a node which is less than 34 with 2. Then we have 36. 36 is greater but less than 67. So 36 should find a placeholder here. So 76 should move right and 36 should come here. So that is what I need to have. But then 76 moving right is also not correct, right? So why? Because if you see here 34, 36 has moved right, but 76 is not between 67. So any node that you move to the top, 34 we move to the top. Remember, we took this and moved to the top. Therefore, it affects this line. These two lines are getting affected. So those two lines, wherever it is, we'll have to rethink and redo that. So while 36 is okay, 76 is not in the right place. So 76 has to actually therefore move. 76 is not between 34 and 67. So 76 is at 67. Now 76, if I take 76 as 67, if you remember, we had moved 67 also to the right. So if 67 was moved to the right, remember we took 67 and 89 and pushed it to the right. That created a problem with this link also. So we have a problem with this link and this link. So before we do 36 movement, while 36 movement is correct because that's what we started off with, but the old placements of 76, 90 and 100 are incorrect, right? So because these 67 and 89 move to the right, so therefore these pointers would now need to point to their correct child, right? So that's what we will have to do now. Now 90, all we need to do is, because they moved right, we will have to shift this also right. So we will have to just say that this 67 to 89 block pointer will now point here, because we moved, because 89 was in the middle space, it was okay, but now 89 has moved to the right. So 90 has to be greater than 89, and 76 has to be between 67 and 89. So therefore we'll have to create a fresh node here for 76 and 89. So let me do that here for lack of space. So I will do a 76 here, which will be between 67 and 89. And I hope you are understanding, because we moved 67 and 89, those pointers have become invalid, right? So 34 went in, for that 67 and 89 had to move right. So all those pointers have become invalid. So we are just trying to make those pointers valid again. So 36 is in the right position, 76 is in the right position, 90, 100 are in the right position. So 36 is inserted. Now where will 53 go? 53 is greater than 34. So 53 will go after 36. So 53 goes here. So this is what you have after this particular insertion, 76 and 53. Now we will insert 51. Now if you have to insert 51, 51 is greater than 34 and less than 67. So 51 has to be inserted here. So 36, 51, 53 will be the sequence. So 53 will have to move to the right. When 53 moves to the right, be careful when you move things to the right. Just now we saw, right? Their child will need to be adjusted. Here there is no child, so we are good. 36, 51, 53 is okay. Then we will insert 12. So 12 will be inserted to the left, and there is a placeholder here. So 12 can be easily inserted here. Then we will insert 10. For 10 we will go left, but 12 has to move to the right. If 12 moves to the right, we'll have to be careful to adjust pointers. Of 12 earlier doesn't have any pointers, doesn't have any child, so this is also okay. The last thing that the penultimate thing that we'll have to insert is 77. So 77 will find a place between 67 and 89. So 77 will come here. And then we will have 69. That is the last node that is inserted. And 69 is between 67 and 89. So 69 will be coming here. So 76 and 77 will move forward, and 69 will come here. And 76 and 77 moving forward means the child node will need to be adjusted. There is nothing in the child, nothing to worry, and we are done with our example. So that is your answer. So that's on this particular topic. On the next topic, I wanted to actually come back and revisit binary tree, where we had left out an important concept, which was the breadth first or level order insertion of a binary tree. In fact, this should not be B tree, it should be binary tree insertion, right? So this is something that is important, and I had not covered it in my last lecture or the last to last lecture on binary tree. Hence I thought that let me take a stab here in terms of converting it out. Now what does this say? That how do you insert things in a binary tree? You know, in a binary tree it goes like this, right? So how is this going to happen? How is this exact sequence of steps going to happen when I actually do an algorithm? So what is happening? I'm going like this, I'm going like this, that is level by level, I'm filling it up and I'm going there, right? So that's why it is called level order insertion or a breadth first insertion. So breadth first or level by level insertion is what a B tree insertion algorithm is all about, right? Sorry, binary tree insertion algorithm is all about. Remember, this is binary tree, not B tree. The algorithm is written, or the outcome of the algorithm is written here, but let us take a small example of between let's say 1 to 5. If we have to insert and create a binary tree, then our binary tree should look like this: 1, then 2, then we should have 3, then we should have 4, and then we should have 5, something like this, right? So how do we use an algorithm to actually make this possible? So the way to make this possible through an algorithm is we will need to build on what binary tree concept usually is. Binary tree concept says that at a particular level you will fill up that level, and thereafter you will actually move on with the next set of nodes in the next level, and that's exactly what we will try to do. So we will say that if the tree is empty, then we will make a new node that is basically the node of the root. So we don't need any queues for that. And by the way, we are going to use queues in this situation to help us create this particular binary tree. So if the tree is empty, then we will just create a node like this. We will just create a double, we'll use a doubly ended array, and doubly ended linked list, and there we are going to actually use a use this 1 will come here as the key, and the left and right child will be null, and this is our root, right? So that's the first step that we will do. Now if the tree is so 1 is inserted, so 1 is done. So let me write the elements we have to do: 1 2 3 4 5. So 1 is done. Next we will have to do a second element insert, and for the second element insert what we have to do is we will have to put the root into the queue. That is, we will have to enqueue the root. So let me create some space and then enqueue this. So I will enqueue 1 into the queue, which is my root, right? So if I have enqueued 1 into the root, then the next step is for me to take a temporary variable and have that temporary variable point to the dq. So the dq is going to give me back 1. So the temporary variable is going to point to 1, right? So temporary variable is pointing to 1. Now the temporary variable, if it is pointing to 1, then the temporary variable dot left, I will check whether it is null. So when I actually dequeue something from my queue, there are two things I will check: whether my left is null or right is null, whatever that node is, right? So I will check whether my left is null or right is null. In our case, our left is null. Then we will insert a new key as the temp left, and then stop. So we will create a new key like this. Let us create a new key here. We will create a new key like this, which is our 2. So we had taken 2, right? We were supposed to insert 2. So we had taken 2, and we will insert that in the temp left. So now it will point here, right? So temp left will be equal to this new key, and we will stop the operation. So this entire thing will be created afresh. Every time we are actually doing this operation or actually doing one insert, we will have to do the operation afresh, right? So operation afresh, and so 1 2 is done. Now we are going to do 3, right? So in 3, again, temp is no more there. So this is the nature of the tree that it looks like right now. After 1 2 is inserted, we are now trying to insert 3. So everything is fresh. Every time you insert, everything is fresh, right? So next time what we will do, we will do a level order scan to get the put the root in the queue. So we will put the root in the queue. First we will put the root in the queue. Now temp we will dequeue, right? So we will dequeue the temp, which is going to give us back with the same thing pointing to 1. because this is going to be dequeued. So this is dequeued. This is no more there, right? So next what we'll do is temp left is null. Then we will insert a new node. But temp left is not null. So we will go and check if temp right is null. If temp right is null, then we will insert the new node as temp right. So we will insert the new node here as my temp right. So temp right will be now pointing to 3, and we will stop because our operation is done. So now again we will start. When we start, there is no more temp. This is our tree, this is our queue, right? So we will go to 4. 4 has to be inserted. Now if 4 has to be inserted, again the same funda, put the root first in the queue, then temp, do a dequeue of temp, right, which will point to the root, because the dequeue is going to bring out this. So temp will point out to this only, right? So temp is pointing there. Now check temp left is null or not. Yes, not null. Okay, if temp next is not null, then the next step is for us to check if the if we can enqueue the temp left, right? So we will, next step for us to, when temp left is not null, right? So we will therefore need to do an enqueue of temp left. So enqueue of temp left, because we'll check the children later. Enqueue of temp left is 2. Remember, we had already dequeued 1. So we don't have anything in the queue. We are enqueuing the template, which is 2. And then we will check that the temp right is null or not. Temp right is null. Okay, I told you we'll check the children later. Temp right is null. Temp right is null or not. Temp right is also not null, as the temp right also has a value, right? So then we will enqueue temp right, right? So these are the two things we will enqueue. Now we will say temp equal to dequeue. When I say temp equal to dequeue, 2 will come out. So temp is now pointing to my 2. So temp is pointing to my 2 now. Again the same concept will start, right? The same concept will start, which is temp left is null. Then insert the new key as temp left. So insert the new key here as temp left, which is going to be my 4. And temp left means this, right? So we insert that, we will stop. So this entire queue is of no use anymore. So this is, let me remove this off, and let us remove this temp. The only thing that is left is 5. So 5 should come here, but how will it come through the algo? Let's see. So put the root in the queue. Okay. Then temp will be dequeued. So temp will dequeue, point to 1. So this 1 is not there. Temp left is not null. Then enqueue. What will be enqueued? 2. Right. Then temp left is not null. Temp right is not null. Then enqueue temp right. Right. So then we will go and do a temp equal to dequeue. So if temp equal to dequeue, then temp will not point to 1. Temp will point to 2 now. 2 is dequeued. So 3 comes here. 2 is dequeued. And temp is pointing where? Temp is pointing to 2, which was dequeued. Temp is pointing here. Again, temp left is null. Temp left is not null. So enqueue 4. Right? Enqueue temp dot left. And then temp left is not null. We had enqueued temp dot left. And if temp right is null, which is our case, right? Temp right is null. Then we create a new node. Insert 5. And we say that temp right is equal to this new node, which means that we are creating this connection, and that's how we are doing this, right? So that's how we have now placed 5 here, and then we will stop because 5 is also done, and in this way it will go on. So I hope you got the message. The essence for you to remember is that we will take the root and we will enqueue it. Immediately we'll dequeue it. Then we'll check the left child of the root and the right child of the root. Left child is null, we'll insert a new thing. Right child is null, we'll insert there also. But if left child is not null, then we'll push that into, we'll enqueue that. And then we'll work with the child. Similarly, if the right child is not null, we will enqueue that. And then we will work with the child. So that is how we will do it. The entire sequence of steps is written here. How whatever I explained on the right is written here. So that's on your binary tree insertion. Now the last key, tree type that we had to do was a B plus tree. Now what is a B plus tree? A B plus tree is where you have, let's say, suppose the problems, let me establish the problem first. Suppose the problem was that if I have X here, and this is a, let us say it is a 4 order key, then M is equal to 4. My key can be 3. So the child here is, let's say, Y, and we have the child here, then we have another child here which is probably Z and P probably, let us say. Now the problem with this approach is that, again, if we have to get the while we got a lot of keys inside one node, which is good, but then we have to still navigate levels, right? We still have to navigate these levels, right, to actually get to what we need. In any event, if we got everything in the leaf node, all my required data points are in the leaf node itself, then our life would have been much easier. And if we can have a link like this, right, so then the life would have been much easier. All we needed to do is position ourselves from here. We will see whether we have to go to this path or this path, right? If we have to go to this path, we can reach Y, and through this pointer we can also go to Z and P. So the entire stack of data we can cover in one shot, right, without having to do any kind of recursion. Only one loop we have to do. All we need to do is reach the correct node. The nodes will reside in the leaf node, and the root nodes will just be or the internal nodes. These are the internal nodes, right? So we have the internal nodes here, we can have another internal node here. All those are internal nodes, but remember, this is my actual data node, right? So everything is here. These nodes are not going to be pointing to any data. I mean, these nodes will not store any data. Rather, they will be routers. They will be routing you to the actual node, right? They will say that, okay, you want to go to 3, then go through this route, or you want to go to 5, then go through this route. This will not store the actual data. It will store only the router. I hope you are getting the concept, and we will get to that. Don't worry about that. So all the actual data are stored only in the leaf node. I told you, right? If we get here, then we can traverse the entire structure and get the actual data set, right, without having to go through multiple recursions. The internal nodes are only used as separators, routers. I told you, right? Internal nodes are only separators or routers. They will just tell you, go here, go there, and we'll see the example. Don't worry. Tree is perfectly height balanced because all the leaves are at the same level. That is also the same. That is, B plus tree is same as the B tree concept in terms of leaves being at the same level. And the nodes have a high branching factor, which is fewer levels and faster search. And the B plus tree, which is also evident from the example that you see. And this typically is used in your databases, indexing, file systems, all of that, where you need a faster access to data, a larger amount of data. Our B tree was solving the problem. It was giving you larger amount of data. But that larger amount of data, if you required some more larger amount of data, you would have to traverse levels. Here, we are not traversing levels. One time we will traverse entire data set we can get. And that's the power of B plus tree. And that's why databases will actually use B plus tree, which is huge sets of data. So if we see what is the difference between a B tree and a B plus tree, then the major difference is what I will highlight here. All of this is the same. What we saw in the B tree versus B plus tree, all of this is the same. But the major difference in the B plus tree is the data is stored only in the leaf node. The leaves are linked within each other. Here the leaves are not linked. The B tree, we did not link the leaf needs. One leaf node was not linked with the next leaf node, right? So there was, if I go back and show you what I'm trying to say, here there was no linkage between the leaves, right? But in a B plus tree, there will be a linkage. I'll show you that. And then what else can we talk about? We can talk about the promotion rule. The promotion rule, we will come to that, right? We will come to that as we move forward. Otherwise, this particular English will not be clear. The rest of the things are more or less the same. Just go through this once by pausing the video. But these are the critical points that I wanted to highlight. So let's do this example. Everything will be clear. We will do B plus tree of order 4 with the following data. So what we'll do is, we will again, M is 4, K is 3, all of that remains same. We saw, right, all the properties are the same except for 1 or 2 properties. So these are anyway the same for a B plus tree. So let's say that I have K equal to 1. K equal to 3 and I have 1. So I took 1 here, I took 2 here, I took 3 here. So I can take all these 3 back to back because I'm inserting in the leaf. Insertion is only allowed in the leaf and my leaf permits me to do so because it has blank areas. So that's on the insertion part of it, of the first 3. Next 4, where will it go? It comes here. So if it comes here, then we will have to make a split of this. So 1, 2, 3, 4. That is what we have in store for us, which is creating a problem for us, right? So if we have to split this, we will just split this in between, right? So we will split it like this. We will say that 1 and 2, you come here, and 3 and 4, you come here. So remember, this split is not going to push things to the top, right? 3 and 4, 3, because the data is supposed to reside in the leaf and this is my leaf. I cannot push the data to the top. Instead, what I will do is I will push this rightmost minimum element. Wherever I split, right, the rightmost minimum element, I will push to the top and I will create something like this. I will say 3 is here. So this 3, don't mistake this 3 as data. This is not a data. This is a router which says everything to the left will be less than 3 and everything to the right will be greater than equal to 3. That's all it says. So I hope you can now understand that why 3 moved up, that is the minimum, so that we can create this balance. And hence, because we are also saying everything resides on the leaf, we have not replaced this 3, we have not removed this 3. We have just said that we are going to move this 3 or keep this 3 here, but make a reference at the top saying that if anybody comes there, they will know that if they have 4, where do they need to go? If they have 2, where do they need to go, etc., etc. So that is what we will do with this concept of this particular 3. Next, we have done with 4, so we are now taking into account the 5th element. Now the 5th element, if we have to insert, then my 5th element will go where? My 5th element can easily come here because my K was 3. So my 5th element can easily go there. My 6th element will come here and that would create an overflow. So what we will do? We will split it. So 3, 4 will be 1 unit and 5, 6 will be 1 more unit. And what we will do? The rightmost split node is this. We will place this at the top as a routing element. Which says that, okay, if you are at 5, then if you come to 5, then the right of 5 will be greater than equal to 5. And the left of 5, it will be between 3 and 5, and that's how this is. And don't forget that we are also creating a link like this as we go along, so that if anybody reaches here, then they can traverse the entire chain of data, right? So that is what we are trying to do. Now next is element is 6 is done. 7. So 7 comes here. So 7 comes here. Now 7 comes here. 7 comes here. Yes, 7 comes here because it was a K equal to 3. Next we will bring in 8. So 8 comes here. We will have to split. So let us split. 5, 6 will remain like this. 7, 8 will become separate nodes. And because 7, 8 became separate nodes, rightmost of the smallest of the rightmost node will go to the top. So we will have 7 going to the top as a router, not as data. Data still remains here. All we are saying is anybody queries 7, they will know that they have to go to this particular branch. Now that is done. Then we have 9. So 9 will go here and 10 will go here. Now when 10 goes here, an interesting thing will happen because it cannot go here, right? If it cannot go here, there will be a split. So 9 and 10 will be split. So 9 will be here, 10 will be here, and our data will be moving like this, right? So 9, 10 going, then we have to take 9 to the top. So we have to take 9 here. So 9 is here. So if 9 is here, remember what is 9? 9 is a router. While the data can be split like this, the routers will have to be split with the old concept of B-tree. B-tree concept was what? This is an overflow. This is an overflow. Yes or no? Yes. So what we will do? Same concept of moving things at the top as we did in B-tree. Not the same concept that we are doing in B plus tree, because we are not working with the data now. These are routers, right? So the routers will have to have a different rule. The same rule that we used in B-tree. So what we will do is we will say that 3, 5, 7, 9, our median is 5, right? So we will move the median to the top. So this we will eliminate for the time being. Pointers we will adjust, and we will say that 3, 5, 7, 9, 5 will move to the top, right? So 5 will move to the top because it is my median, and 3 will be less than 5. 3 will be less than 5. We will keep placeholders here. Then we have 7, which is definitely going to come here, and 9 will be coming here because it is greater than 5, right? So this is something that we have achieved from a splitting of the routers, separators. Now let us adjust the pointers. 1 and 2 is less than 3. Now 3 and 4 is greater than, equal to 3. 5 and 6. 5 and 6 is less than 7. Right? So 5 and 6 will be less than 7. Five and 6 is less than 7. Right? So it is less than 7. And then 7, between 7 and 9 is 7 and 8. And this is greater than 9. So this is how you will build a B plus tree. If given an example like this, you will just remember that at the leaf layer, you are going to split and add routers at the top, which is the rightmost split elements minimum value. Those are not the actual data, they are just routers. And if the routers themselves get filled up in their nodes, then we will split it with the same logic as what we did in B tree. Right? So that's something that we will need to remember. And I think that's all that we had in store from this chapter standpoint. What are the properties we have discussed? Does a B tree grow at its leaves or at its root? Where do you think it grows? A B tree will always grow at its root. If you remember when we said this, right? So yeah, see this example. What happened here? We were here, we went here. What did we increase? We increased a node here. Where was the node added? At the root. So B tree grows where? Bottoms up. Right? So it will always grow bottoms up. Don't think that we said it will get added to the leaf. That's why the leaf is at least at the same level. You're not growing anything. You're utilizing that same level. The growth happens here like this. Because if you are actually struggling for space here, you will create nodes here. Struggling for space here, you will create nodes here, and so on and so forth. And that's why we will say that the B tree growth will happen at the root and not the leaves. Right? So this is something that please remember. We discussed this also. Purpose for which B trees are appropriate, we have discussed that. B trees are typically appropriate for the access of elements or memory from a disk. That's typically the root. And this is a question we have already done. Right? When we did the B tree of order 4, this is a question we have already attempted. It had come and we have already attempted that. Let us attempt to do this B tree problem. It's kind of long, but let's attempt to do that. I think the concept that we have learned in B tree will be clear from this example. So what do we have? M is 4, K is 3. So let us take the 3 key node and we can directly insert 84, 82, 29 because we can insert into the leaf. The leaf is the first node and the first node already has 3 positions. But we have to be careful to insert it in an ascending order. So 29, 82, 84, right? So that's what we will have to insert. Next, the element that is coming in after this is our 97. So 97 will create an overflow here. So the overflow getting created is written here on the right so that we identify the median. So the median is identified as 82. So if we identify the median as 82, then 82 will need to move to the top. So we will remove this. We will track it from the right. We will say 82 is moved up. New node is created with 3 keys and we'll accommodate 29. 29 is to the left of 82. So 29 is to the left of 82. 84 and 97 are to the right of 82. 84 and 97 are to the right of 82. So that creates this particular accommodation of 97. Next we have 61. So 61 will get inserted here, which is okay. Then we have 10. Now 10 will get inserted to the left, but to insert 10 I have to move 29 and 61. So I will move 29 here, 61 here and 10 here. So that is something that will make us space for 10. After that we have 45 coming in. Now 45 coming in will be coming in here. Actually it will come in here in between, right? Because we have to take it in sequence. Now we will not worry about this because we will anyways write it here. 10, 29, 45, 61. Median is identified as 29. We will remove this block. We will create this 29 as a node, right? And then we will adjust. So we will create, in fact, my bad. In fact, what did we have? We had like this, right? So 21 will have to move up. It's not that I'm creating 29 fresh because this is not the first node. The first node we created 82 fresh, which is fine. But when we have an overflow at the internal node, then we are moving the median up. So the up median 1029 will find a space here. So 82 will need to move to the right. So 29 will be here, 82 will be here. So remember, only when you are at the root, you can create new node at the top for the median. But you are not at the root. This is not the root. So the median has to go to the top node. Right? So 29, 82 is fine. Now let us remove this particular block. And let us see that what kind of situation we get from the remaining elements that we'll have to fulfill. So we have taken 29. We now need 45. So 45 and 61. If you see 45 is greater than 29. In fact, we missed out on 10. Let us do 10 first. 29 we have moved up, which is fine. 10 is left. So 10 is to the left of this. And 45 and 61 is to the right. But 45, remember we had pushed 29 here, right? And that's where 82 was here. So if 82 was here, this link was actually to the right of 82. Now it has become to the left of 82. Therefore, this link is no more valid, right? So what we will do, we will push this link here. So 82, 84, 97 is the link. And 45 and 61 is between 29 and 82. So we will use that link. So 45 and 61 is coming from here. That is what is happening when we insert 45. Next, we are inserting 28. 28 will find an easy place here. So 28 gets inserted here. Next we are inserting 49. Now 49 is greater than 29, less than 82. So 49, we will push this 61 to the right. When we push, we have to be careful to the links, and the links are not here because this is a child node. Insert 70. Now 70, where will we insert? We will insert 70 here. Overflow. So let us write it here. 45, 49, 61, 70. So let's be careful because the tree is growing. Let us be careful when we are trying to now make adjustments. 49 is my median. So 49 will have to go top. So when 49 goes to the top, what we are doing? We are adjusting 82 going to the right. When 82 goes to the right, what happens? Child pointer will need to be adjusted. So 49. So we'll have to be careful for all the child pointers. Let us see for all the child pointers. Now here, this we will remove, and the child pointer is something we will adjust. Right? So for 29, 84 and 97, they are greater than 82. So that means that this is the pointer. Now 45 we have to insert. 45 is between 29 and 49. So we will insert 45 here. This is done. 61 and 70 we have to insert. So 61 and 70 is where? 61 and 70 is between. Let me make some space. Yeah. Okay, so now we have to insert this 61 and 70. Now 61 is greater than 49, less than 82. So 61 will be like this. 61 and 70. So can I therefore say that if I want to just do the small change so that things look a bit better, then I'm saying that we have taken this here. I think this will be looking better, and we will also push this up like this. Yeah, so this is, I think, much better to look at. Now the next element that we are inserting is 70 is done. So we'll be inserting 86. So 86 will find a placeholder in this 84, 97 bucket. So this 97 will move to the right and 86 will come here. Next 68. So 68 will come in 61, 70 bucket. So it's 68 is greater than 49, less than 82. So 70 will move to the right. 68 will come here. 70 will be going here. Next, next the insert that we are going to do is on, where were we? I lost track. So we did, I think we did till 68, right? So we have done 68, 61, 68, 70. We are now into 19. So the 19 will go into this area, right? Less than 29. So 19 will go here. And what was there? 19. Then we had 28. Okay, so that is done. Next we have 55. Now 55 will go into, where will it go? Let's see, 55. So 55 is between 49 and 82. So of course it will go in this side. So we'll have to write this here, overflow 61, 68 and 70. Right, so 55, 61 will have to go up, which is my median. So we will remove this, and at the top we have to create something. So this 61 now creates a problem. Why? Because this 61 goes here, right? 29, 49, 61, 82. It has to go up, right? So therefore our next set of adjustments come in, which is 29, 49, 61, 82. And this set of adjustment, we will create a new node because we are moving to from bottoms up, and we are creating a new node, because here we have a overflow. Here we have a overflow. So we had an overflow here, and which created an overflow here. Right, so that's why now we will now be creating 61 or adjusting 61. To do that, 49 is our median node. Right, so 49 is our median node. So 49 will move to the top. I'm just drawing this fresh. 49 will move to the top, and from 49 on the left side we will have 29. On the left we will have 29. On the right of 49 we will have 61 and 82. That is a no-brainer. On the right we will have 61 and 82. And then what we will do is we will adjust the left, which is now 29. We can immediately adjust what was here, which is 10, 19 and 28. No changes there, because 29 has not changed. Left node of 29, left child of 29 will not change. The right child of 29 will also not change, which is 45. It will remain like this. And then 61, 82, the left of 61, the left of 61 will be okay. Now we are done with this. I think 29 is done, 61 is done, 82 is done, and we were doing the left part of this, which is perfectly fine. So we have taken care of this, we have taken care of this, we have taken care of this. What we have to take care of this, right? What we actually removed from the top. So that creates us gives us an opportunity to take 55. So 55 is less than 61. So then we have to create it like this. 55 is less than 61. So it comes here. Then 68 and 70 is there, which is in between 61 and 82. So then 61 and 82, in between that we have to create 68 and 70. Right? So that is also done. And then we already had this, which is 84, 86, 97. So this comes from here. So which is our 84, 86, 97. So that takes care of our insertion for this particular item. So let me remove this. No more required. This is how our tree looks right now. I hope you are getting where we are going towards. Now 22. 22 has a place where 22 doesn't have a place. Why? Because 22 will have to get inserted here. Here 22. Right? So that creates me an imbalance. 10, 19, 22, 28. So in order to adjust that, we will remove all of this. 22 will move to the top. 19 will move to the top, which is my median node. This 19 to move to the top will need to remove 29 from its position. So our 19 will go here. Our 29 will be after 19. And then we should also have our original nodes. And this pointer we will change, right? Because this pointer will now change because 29 has moved. So this pointer is no more valid. This pointer will be now pointing here. This pointer will now point here, right? So, and then we have to adjust our 10. So 10 is here. Then we have 19 is already gone up, 22 and 28. So 22 and 28 is in between 19 and 29. So 22 and 28. So that is how this comes. So we have 10, 22, 28, 45, 55, 68, 70, 84, 86, 97. Then we insert 11. So if we insert 11, where will it go? Let's say we have to insert 11. 11 will go to the left of this, left of this, left of this. So 11 finds a perfect place here. Next we have to insert 55. Now 55 is a duplicate, so what? 55 could be one more data, insert it here, right? So that is also done. Now 77. 77 is going to go here, right? So 77 is also done. And then comes 16. 16 also we have a placeholder. And that completes this example. So as I said, it will take some time, but then this is how typically you will do it. Don't forget one important step, that when you are splitting things, in fact two things, when you are splitting things in the internal level, you will split it you will have to take the median to the top. In the root layer, if you are splitting it, you can create one more node at the top. For the areas where you are shifting the keys to the right, be careful on the child pointer shiftings, right? So that is also important. We have discussed this. We have discussed this also, right? So that is also discussed. And then in a B plus tree, both the internal nodes and leaves have trees. Actually, no. Only the in B plus tree we have the actual elements in the actual data elements in the leaves and actual routers in the internal nodes. So both internal nodes and leaves have keys is actually false. Right, so write the difference between B tree and B plus tree. I've put some differences here, but the main difference is we have already seen earlier, right? So we had already highlighted the main differences in which we said that everything is in the leaf for a B plus tree. The leaves are sequenced, so if you go to one leaf, you can go to everything else. So that is one more difference. The internal nodes are routers, there the internal nodes are data. The rest of the differences are here for you to read. And the last example we had is on an AVL tree. So let us complete this also, just to make sure that we can complete what we wanted to cover. Let me see if this is the last example. Yes, almost the last example, but let's see if we can also cover this out. So for this example, we have to construct an AVL tree with explaining the rotations, of course, yes. So let us take 17 as the first node, 25 will go to the right. Remember, an AVL tree is a binary search tree. 19 will go to the left, and there we have a disbalance, and this disbalance is because we have created a right and a left. So when we have a disbalance of right and left, I told you alphabets are different, so we do the same things that the alphabet wants us to do, one right rotation and one left rotation. So let us do one right rotation at the junction point, right? So if you do a junction point rotation, then we will have 17, 19, 25, and then because this is also an imbalance with right, so we will have to do a left rotation, which is this rotation that we were talking about, right? So we will do a rotation for 19, 17 and 25, right? So that's our current position of the tree. Then we have 23, which is going to go to the left of this. Then we have 75, which is going to go to the right of this. Nothing is disbalanced yet. And then we have 6, which is going to go to the left of this. And I don't think anything is disbalanced, and that's the answer. So only one disbalance was there and we solved it out. So that's on this particular example. Then we have write short notes on AVL tree. Don't forget to say that it is a binary search tree. It talks about the levels, the difference between the heights to be between -1, 0 and 1, and that's both the things that you have to talk about. Give an example, and that's it. Maximum possible height of an AVL tree with 7 nodes. So let's see how many things that we can, how many nodes can be used to draw, or rather, how with 7 nodes, what is the maximum height that we can reach, right? So if we have 7 nodes, then we can actually do something like this. We can actually do a standard perfect binary tree. This is 7 nodes. This is 7 nodes. How much height did we achieve? We achieved height of 3. But does that mean that with 7 nodes we can only achieve 3? That's on a perfect binary tree. But AVL tree is one step beyond, right? It gives you some amount of leeway. Leeway in the sense that, okay, you are allowed to have this. Need not be perfect, because one level of gap they allow, and that's why it says height of left subtree minus height of a right subtree should be, if I take the modulus of it, it should be at least less than equal to 1. That's what it says, right? So it gives you a gap of 1, right? So if it gives you a gap of 1, then of course this 3 should become 4. That's a simple answer, right? But then how can we prove that such a tree really exists where I can increase my height to, let's say, 4 and yet use 7 nodes, because with 7 nodes I saw that I'm going to get only 3, but definitely in AVL tree, because we have some amount of relaxation, we can actually get something like this. We can do this, and then we can do this and this. So there you go. You have something which is utilizing how many nodes? Let me see if I got my nodes wrong. 1, 2, 3, 4, 5, 6, and we can also have 7 here. Yeah. So with this, you can actually get your nodes created in terms of a height of 4, because you have this particular node. If you see the height of this, it will come here as 1, 2, 3 and 4, the longest path, right? So that's where you get a height of 4 from nodes as 7. And is there a general formula for this? For node 7, total nodes of 7, I can get the height of an AVL tree, the maximum possible height, as 4, right? But then is there a general formula? Because in this you will not see any disbalance. That means it is an AVL tree. Now if there is a general formula for this, then we can actually calculate it very smoothly. So the general formula is NH is equal to NH minus 1 plus NH minus 2 plus 1. That's the general formula. So with the height of let's say 3, if I put height of 3, then N3 is equal to N2 plus N1 plus 1. Right? N3 is equal to N2 plus N1 plus 1. Now N1 is treated as 1 and N2 is treated as 2 in most of the textbooks. Right? So from a node counting standpoint, but both forms will lead to the same sequence. Sometimes you will say node 0 leads to 1 or node 1 leads to 2. Sometimes they say node 1 leads to 1 and node 2 leads to 2. So we can substitute these values, that is 2 plus 1 plus 1. So we get 4. So height 3 is coming from 4 nodes, right? So height 3 is coming from 4 nodes. For height 4, if we say height equal to 4, then my NH is equal to N4, which is equal to N3 plus N2 plus N1, and we have N3 plus N2 plus N1. We calculated N3 as 4 from the top. N2 we know is 2 and this is 1, so this is 7. So with 7 nodes I can get a height of 4. And likewise I can calculate N5. N5 is going to be N4 plus N3 plus plus 1. In fact, here I should have put 1. Though it won't make any difference, but that's what we need to do from a consistent standpoint, plus 1. And then we have N4 as 7, N3 we have as 4, and 1 is 1. So that takes us to 12. So that is how we will calculate if given an unknown problem. AVL tree differ from binary search tree pretty simple, because all AVL trees are binary search tree, but all binary search trees are not AVL tree. One difference. What is the extra thing that AVL tree has? The balancing part of it. Binary tree doesn't have that. Put that as a difference. Rotation is used. Put that as a difference. Where is it used? Fast lookups for AVL tree, and fairly balanced data is for binary search tree. It is AVL tree is of course more complex to implement, and the BST is easier to implement. So that way I think you can answer a lot of differences from this particular question. So that's pretty much that I wanted to cover. So trees we have covered at very length, and I've covered all the questions that is possible from a standpoint of any university examination in a undergraduate BTech course. I hope this would be helpful for you to probably crack your exams in a much better way. Until the time we meet next, happy learning. Thank you.